시작을 좀 해야겠네요. 기다리려고 했는데 5분 지나버려가지고 조금 애매하네요. 자, 그러면 검용 수업에 들어가면 자, 게시판. I wanted to basically show you what it was supposed to be if you didn't see the results from previous sessions. So if you draw a streamline from plane A to plane B, it's really important to define those planes. You're going to see this amazing streamline, and you'll see the velocity. But I think the problem last time was that the domain was not properly defined. Wait, am I? Yeah, sorry. This was vector and this was streamline. Sorry. For the vector, I think the problem was that the domain was not properly defined. So please, if you're post-processing the results, make sure you're defining a proper construction domain, either in plane or volume, to present these values that you were interested in. 혹시 문 좀 닫아주시겠습니까? 감사합니다. And on top of it, okay, so we learned, well, not necessarily we learned, we tried to model a pool boiling simulation last time, and not many students saw the results, but we have 2 students, or more than 2 students, who reached to the final step. So as we post-process, it looks just like this. So this is after what was it, ANSYS Fluent. We defined a result cell, and then we saw the vapor volume fraction. So this will be in animation. So I just want to show you that this actually works, right? Just in case, you don't have trust in me. So okay, so you're seeing the time go by, and then the bubbles nucleate at the bottom of the cells, and then they depart with this sort of dynamics. So again, I'm not giving you a random material that doesn't work. I'm giving you a material that does work, and precisely, wait, so this was, oh yeah, that was volume fraction. This one's velocity contour. So, what was it? As bubbles are formed, you're supposed to see vortices around the bubbles and turbulence around it. So if you see these 2 videos in parallel, you can see it's the bubble growth that involves a lot of liquid vorticities. So yeah, right? Remember, this is where the bubble departs, and this is where the liquid quenches under the micro layer. So boom. And then there's the velocity domain, right? Because there's the, what was it? There's the evaporation and condensation at the interface happening. So again, I think we should do the 3rd one first, and then we're gonna do a 2nd one, because I think the 2nd one needs sort of some sort of examination. So today we're gonna work on flow boiling. If you go to the last section, I think it's page, I don't really know the page, 181. You can see flow boiling with ANSYS Fluent, and you're gonna do pretty much similar thing, just like the last session. And then you're gonna get rid of the volume and then create a face. And then after this face, you're gonna define the inlets and outlets. And with these name sections, if I'm missing any detail, please let me know. I hope it doesn't miss any detail, but you can also size the mesh within the domain, and then you can smooth out the mesh elements. So when you finish your meshing step, it has to look like this. So it's more refined at the bottom, and the inlet and outlet. And check the mesh quality, because it has like progressively refined mesh at the boundaries, so it doesn't reach 1, unlike the first simulation we did. Of course, you're going to connect it to Fluent, and then of course update the mesh, launch Fluent, and here you can see these boundary conditions applied. So of course the two fluids that are involved here are liquid and vapor, liquid water and vapor water. And then the heater substrate is of course copper. Copper has really high thermal conductivity. So what is it? So we're going to choose these models to implement this phenomenon, and then for these you're going to also apply the evaporation condensation mechanism from Lee model. So after this, you're going to give this heat flux of 500 watt per kilowatt per square meter. These values are not randomly chosen. Again, these are physically based on experimental results, so that you can see a proper flow boiling phenomena. So of course you're going to give the inlet velocity, and then it's going to be the pressure boundary at the outlet. So once you set up these conditions, of course you can use the patch to initialize the variables. Certainly, by typing in the initial values, the initialization step has to be completed. But I was a bit nervous. I wanted to make sure that these patch variables help the initialization process. So this doesn't really have to be called pool, by the way. So, and also top lid will be adiabatic, and then you're going to run the simulation. So if you reach here pretty quick, please leave the laptop on so that I can see the results, and then I can get the video out of it. This was supposed to be a video, but I somehow got rid of it unfortunately, so this is not a video anymore. But at least at this point, I also expect this will be somewhat similar to what we did in the last lecture. So again, if you missed the video, here's the vapor volume fraction. So by giving the proper heat flux boundary condition, we reach the pseudo boiling phenomenon. Boiling is a really interesting phenomenon, I would say, and I spent tremendous amount of time studying boiling and related mechanisms per se. And if you can see here, there are a lot of key parameter statistics related to boiling. You can see here within this 4 centimeters of domain, there are 3 bubbles generated. So the nucleoside density will be 3 divided by the area projected. But this is a 2-dimensional cross section. So if we're going to analyze the bubble diameter here and nucleoside density, we would have to assume another dimension in the perpendicular direction. So here you can get the bubble diameter in terms of 2D polygon, and then by what was it? By converting the polygon area into an equivalent circle, you should be able to get the diameter of the bubble. Also on top of it, here what you can see is we're using volume of fluid method, and it's based on the diffusive interface between the liquid and the vapor. So when you actually take a look into this, what it really means is, imagine this is a fluid cell. Let's say there are 9 fluid cells, and then it's not 1 to 0 direct jump, but it's rather 0.8 to 0.7, then 0.5, and then 0.3. Let's say, so with these values of the vapor fraction, we should be able to reconstruct the interface, and it's gonna look like something like this, right? And then at each point, the direction, the normal vector of this this interface has to align with the direction of this interface. So this is how we reconstruct these. What was it? Liquid vapor interface from these volume of fluid values given. So there are a lot of tremendous research related to this as well. One of them being neighbor search for each mesh cell, so that they can calculate the easiest way or the least time consuming way to calculate the location of the interface and the direction of those interfaces. And then especially the problem gets significantly more complicated as it extends to 3D simulation, especially transient, because the interface has to be calculated at each time step. So there's a lot of research around this domain as well. So this is one thing I want to share. And what was it? I'm not getting these values out of nowhere. Again, when you look at water boiling curve at one bar per se, the boundary condition we used was 100 kilowatts per square meter. So it's here, right? And then that's when the bubble rises to the surface. So that's our simulations are based on actual physical phenomena. And here, with the flow boiling simulation, we also did a proper estimation of the boundary condition. Flow boiling, what was it? Flow boiling curve, let's see. So for flow boiling, we can also see these heat fluxes somehow relate to the single bubble regime or the nuclear boiling regime, and then that's what's being simulated here. So again, if you're simulating a thermal physical phenomenon, make sure it aligns with the actual practical experimental results, or at least the conditions at which those experimental studies are conducted. So keep that in mind, and then we're gonna go to this flow boiling simulation and see if we can work on this. So please take a look at it, and if you have questions, please ask me, and if I'm missing any steps, please ask me as well. Well, sorry, maybe. I think we have the results. If you finish the simulation properly, it should look like something like this. So, again, this is how it should look like. So yeah, please work on this. 규동. 어때? 여기도 있어. 어때?